Hello, my name is Roy Simpson. I'm a professor of mathematics at Cosumnes River College in Sacramento, California. This is a lecture for intermediate algebra on quadratic models, specifically using data points to create quadratic models for specific situations. This all pretty much comes down to one idea. Use a system of equations to build your parabola or your quadratic model. And we'll do this, we'll show how to do this by doing a basic example where I just give you 3 points and tell you there's a parabola that goes through these 3 points, and I want to know what is the equation of that parabola. Now, this was mentioned in a previous lecture I gave on the vertex form. There's 3 possibilities when somebody gives you some data where you can build the quadratic equation that yields that data. The first thing is that they give you a vertex and a point, and that's all you really need to build a quadratic equation is a vertex and a point. So if somebody does that, if they give you a vertex plus a point, then you're good to go. You can actually use the vertex form to build your quadratic equation. However, in any other situation where you're just given 3 points, then you must, actually I wrote that kind of backwards. In any other situation where you're given 3 points, you must use a standard form of an equation. Now sometimes it's a little bit easier than others, but the ones we're going to deal with today in this lecture are all dealing with the standard form of the equation y equals ax squared plus bx plus c. Now, I happen to know that each of these points satisfies this equation. So what I'm going to do is I'm going to let x equal 1 and y equal 1. And when I do that, I get a system of equations, or I get an equation like this. Y is 1, a times x is 1, plus b times x is still 1, plus c. And of course, then I can go ahead and let x equal 2, and therefore y would be 3. So let's plug that in. When y is 3, x is 2. And then finally, when x is 3, y is 9. So I'll plug that in. And what you see here is a system of equations. There's actually 3 equations here with 3 unknowns. Now I'm going to clean this up a little bit, and I'm also going to write it in reverse order. In other words, swap sides here. But in my cleaning process, I get this. 1a plus 1b plus 1c is equal to 1. 4a plus 2b plus c is equal to 3. 9a plus 3b plus c is equal to 9. There's our 3 equations and 3 unknowns. And now we can start solving this system. And I'm going to choose to kill off the c variables here. That's my choice. So what I'll do is I'll take I'll take row 1 and add that to negative row 2. So let's take row 1 and subtract off row 2. You'll get the following: negative 3a minus b is equal to a negative 2. That's just taking row 1 and subtracting off row 2. Now I'm also going to take row 1 and subtract off row 3. Subtracting row 3 is the same thing as adding a negative row 3. So row 1 minus row 3 gives me a negative 8a. b minus 3b is a negative 2b. c minus c cancels by design. And finally, 1 minus 9 is a negative 8. So we get a system of 2 equations with 2 unknowns. I'm actually going to multiply both sides of the top equation actually by a negative 2. So negative 2 times this new row 1 will become the very new row 1. So I get the following. 6a plus 2b is equal to positive 4. And now I'll go ahead and add these equations up. And I get that negative 2a is equal to a negative 4. If you've forgotten how to do all this, you can go back to my lectures on, there's a playlist I have called Lots About Linears, and there's a lecture in there on solving systems of equations. Divide both sides of this equation by a negative 2 and you get that a is equal to positive 2. Since I know that a is positive 2, I can then use that to find b. I'll just substitute that maybe into this equation right here, because that just looks like a nice easy equation to work with. So let's see, negative 3 times that positive 2 plus 2 is equal to b. All I did was add b to both sides and add 2 to both sides, swap those sides. It's a negative 6 plus 2, that's a negative 4. So b is a negative 4. And finally, since I have a and b, I'll plug that into any of the initial equations. In fact, I'll plug that in the very first equation. So I get 2 minus 4 plus c is equal to 1. That would be a negative 2 plus c is equal to 1, or in other words, c is equal to 3. I'll highlight that as well. What does this mean? It means that our linear equation, or not linear equation, our quadratic equation that graphs and goes through 1, 1, 2, 3, and 3, 9 is of the form y equals 2x squared minus 4, oops, not b, but x plus 3. And that's how all these are done. They're all, whenever you're modeling quadratic data, you essentially are solving systems of equations. You're just starting with a system or an equation of a quadratic in general form, and then you're substituting in the points they gave you. Just to demonstrate that this always works, let's try this again. We have another parabola that passes through these 3 points, and I know the equation of a parabola is a quadratic equation of the form y equals ax squared plus bx plus c. I happen to know 3 points that satisfy this equation. I will plug them in. And I will write that actually, well, I'll write it in this order. So when y is 1, x is 0. So I'll have 0 plus c. When y is 7, x is 3. So I'll have 9a plus 3b plus c. And when x is 4, y is 5. So y is 5, x is 4. That becomes a 4 squared is 16a plus 4b plus c. And now let me go ahead and clean this up. One thing I want to mention here is that this equation actually tells us what c is. It tells us that c is equal to 1. So if you wanted to, you could rewrite this system. It's not that necessary actually, but you could rewrite this system right now to reflect that you know c is equal to 1. If you want to do that, since we're already cleaning it up, you're more than welcome to. That'd be 9a plus 3b. And instead of plus c, it would have been a plus 1 equals 7, right? But I'm going to subtract 1 from both sides, so I'll just do that all in one fell swoop. I'll subtract that 1 from both sides to become a 6. And the same thing with the second equation. We have 16a plus 4b, and it was going to be a plus 1 is equal to 5, but I'm going to subtract 1 from both sides to get me this. And this will be our system of equations. Since we already know what c is, I can just highlight that and we can continue forward. Alright, so we have to choose a variable to kill off. I think the b's would be very easy to kill off here. I'll take, I'll write this in red, I'll take a negative 4 and multiply that by row 1, and I will add that to a positive 3 times row 2. So let me write those equations out, those temporary equations. I get a negative 36a minus 12 b is equal to a negative 24. Don't forget to multiply both sides of row 1 by that negative 4. That's a very common mistake. And now I'm going to multiply both sides of row 2 by positive 3. That's 30 plus 18 is 48a plus 12b is equal to 12. And now I'm going to add these two rows together. A negative 36a plus 48a is actually a positive 12a. The b's cancel by design, equals a negative 12. In other words, a is equal to a negative 1. Let me highlight that. And now that I know what a is, I can use any of the previous equations to find what b is. I'm just going to go ahead and use that equation right there. So I see that 9 times a plus 3 times, wait, that was wrong. I know 9 times a, which is a negative 1, often happens that I make little mistakes, plus 3 times b is equal to 6. That's a negative 9. I'll add 9 to both sides. I get 3b is equal to 15. Divide both sides by 3. I get b is equal to 5. So again, you see, not so hard to actually build these. The quadratic equation that yields the parabola that goes through those 3 points is going to be a negative x squared plus 5x plus 1. Now this is a problem I really kind of enjoy. So even though I found this in a textbook and it's kind of in a lecture section in a textbook, I still like to use it. Francine has designed a synchronized fountain display for a hotel in Las Vegas. For each fountain, water emerges in a parabolic arc from the nozzle that is 3 feet above the ground. Francine would like the apex of the arc to be 8 feet higher than and 2 feet horizontally from the nozzle. That's kind of weird language at the end. But what I'm doing is I'm going to go through this problem-solving process. I read the problem. I think I understand what's going on. We got a water fountain. But just in case I don't understand, I'm going to go ahead and draw a picture here. So let's see. I'll pretend that this is the ground. And let's see, we have water emerges in a parabolic arc from a nozzle 3 feet above the ground. So we'll pretend that here's a little pedestal and here's a nozzle. Okay, and water fires from this nozzle in a parabolic arc. And this nozzle, the water leaves it at 3 feet above the ground. She'd like the apex, in other words, the highest part of this, to be 8 feet higher than the nozzle. So in other words, I want this apex to be at 11 feet off the ground, because the nozzle is 3 feet off the ground, and 2 feet from the nozzle itself. So there's a picture of the situation. I kind of figured out, I think, what's going on, right? We can draw a set of a coordinate system on this if you wanted to. If you did that, you would essentially say that you have a parabola that initially is at a height of 3 here, climbs and falls. This, where it starts falling, basically the apex, is at x equals 2, y equals 11. Now remember what I said at the beginning of this talk. I said if you are given a vertex and a point, that's all you need. The previous two problems we needed 3 points, but here a vertex and a point is perfectly fine. So let's see. Francine would like. Okay, so I'm assuming that they're just asking us to write an equation for the situation. So the third thing I'll do is label unknowns, but I kind of already have. My unknowns here are x and y. So I'm just going to use x and I'm going to use y. Or you could use h actually. Let's use x and h. X being the horizontal distance and h being the height. That sounds fun. And now the fourth step is always create equations. So let's go ahead and do this. And if I try to make a system of equations here, it doesn't work out very well because I only have 2 points. But, well, technically I have 3 points. I do know something else about this. I do know a little bit about symmetry here. If this is on my parabola, and here's my vertex. Vertex, remember, is like the mirror point. So you know that there's another point that exists at a height of 3 over here. And it happens to be 2 units away from the center, just like this other point here is 2 units away. So I suppose that you could do a system of equations involving those 3 points. I'll tell you, it's a little bit faster actually to use the vertex form of a parabola here. Remember, the vertex form of a parabola is going to be h equals, I can't use h actually, well, h is equal to a times x minus, we'll use the letter r squared plus k. The reason why I had to change up letters is because h is normally used for that center letter right there, but we're using h as our height variable. In this case, the values of the x and the y value, or the input and output values for the vertex, are 2 and 11. So I'll plug those in, or substitute those into our equation here. H is equal to a times the quantity x minus 2 being squared plus 11. And now I see I'm only missing one more piece of information, and luckily I have a point. Not only did they give me the vertex, they gave me a point. So I'll let x equal 0 and y, or h, equal 3. So my output is 3 when my input is 0. And now I can solve this. This is going to be 4a. So we get 3 is equal to 4a plus 11. Put a lot of implication signs in here. Subtract 11 from both sides. So I get a negative 8 is equal to 4a. And then divide both sides by 4. You'll get that a is a negative 2. So my equation here, which I'll steal from right there, is going to say the height of the water should be given by negative 2 times x minus 2 quantity squared plus 11. Perhaps she has to plug that into some type of computer or something like that so that it knows how to aim the nozzle, whatever it may be. But that is the equation that the water follows. As a final example on quadratic modeling here, because it's all pretty much the same thing, we have this what looks to be a tough looking problem because there's just a lot of words. People get intimidated by that. Let's read through it. The cables on a suspension bridge hang in the shape of parabolas. Imagine a coordinate system superimposed on a diagram of a suspension bridge. Suppose that's just some advice. Each of the towers is 500 feet high and the span between the towers is 4,000 feet long. At its lowest point, the cable hangs 20 feet above the roadway. Find the coordinates of the vertex, one other point on the cable, and use them to find the equation for the shape of the cable in vertex form. Okay, that's a lot of wording. But we've read it. I kind of understand what's going on. We got a suspension bridge. I'm going to go ahead and draw a picture, though, so that I can get an accurate idea. We have these towers that stand, and they're 4,000 feet apart. That. And each tower is 500 feet tall. And there's a cable that hangs between them. It comes down actually pretty shallow. It comes down and then climbs back up. Just do this. And it tells me that the distance when it reaches its lowest point is just 20 feet above the ground. And now I'm supposed to model this using a quadratic equation. All right, well, since they didn't tell me how to superimpose this on an axis, they just told me this is what the shape of it is, I'm going to actually create my y-axis to be right here and allow my x-axis to be right here. Reason why is because if I can avoid having my vertex off of the y-axis, I'll take that option. I like this, that it's symmetric, and I don't know, it's just nice. So this point, the vertex here is at x equals 0, y equals 20. And this point right here is, well, the x value is not going to be 4,000, it's half of that. We've only gone half that 4,000 over. So it's at 2,000. And the height is going to be 500. We have a vertex and we have a point. So now we can go ahead and solve this. By the way, the next step normally in the problem solving process would be to label our unknowns, but we already chose x and y. And fourth thing is to create an equation, but that's what we're doing here. We're creating equations right now. I know that the vertex form of a parabola is y equals a times the quantity x minus h being squared plus k. And we know the vertex of this parabola occurs when x is 0 and y is 20. I'll plug those in. Actually, I don't need even a parenthesis because x minus 0 is just x. So this is going to be x squared plus 20. And finally, I need to find this value of a right here. And I can do that by plugging in another point on the parabola. And we just said we have a point at x equals 2,000, y equals 500. So I will allow x to be 2,000 and y to be 500. In this case, I'll subtract 20 from both sides. So I get 480 is equal to a times 2,000 squared, which is 4 million, I guess. And now I'll divide both sides by that 4 million. And I will get that a is equal to at least 48 over 4, 1, 2, 3, 4, 5. So 400,000. And technically, I suppose I could reduce this even further. Both top and bottom are actually divisible by 4. I know that. That's 12 over 100,000. Both top and bottom are divisible by 2. That's 6 over 50,000. Both top and bottom are still divisible by 2. That's 3 over 25,000. That's a skill you should always retain, is reduction of fractions. So I now know that my equation, I'm just going to replace a with 3 over 25,000. So the dominant equation here is y equals 3 over 25,000 x squared plus 20. And that is the quadratic equation that will be used to model the shape of this parabolic shape. I guess is the best way to say it.